Yeah, hi everybody. Great to be here. I'm Diederik. I'm Chief Scientist at Allora. And before I start, I really want to thank Jo for putting on this awesome meeting. I've really been learning so much this morning, and I'm sure it'll be a lot more. So I really appreciate it. Also understand that this is like a one-man effort to put all of this together. So maybe give Jo a round of applause. So one thing I find amazing about these types of meetings is that you can't really, study to get here. So everybody in this room has a very different background, right? You talk over coffee and it's like, oh wow, didn't really imagine that. So I'm an astrophysicist by training. I published over 300 papers in astrophysics, and then I got bored. The universe is not in for that. Kind of ran out of interesting things. So the cool thing about astrophysics, though, is that it's sort of characterized by extremely low signal-to-noise data. So you kind of have to draw rather far-reaching conclusions from way too little information. And that sounds very familiar, doesn't it? I think a lot of the things we're discussing today is actually related to that. So when I got bored, I decided, okay, I think there's actually something really interesting to do in general in AI, and then specifically into decentralized AI, what we're talking about today. And decentralized AI in particular is just getting more and more urgent and more important every day. And not just ideologically, I think a lot of people here will align on that, but also functionally. It turns out decentralized AI actually has the potential to be a lot more accurate and a lot more impactful than any individual model. And that is one of the main things that I'd like to demonstrate in the talk today about Allora. Before I get into that though, let's talk about empires a little bit. Now that we are in this beautiful city with beautiful buildings like this one, I don't know if any of you went on an evening stroll yesterday, but you might well have come across this beautiful place. This, of course, is a relic of the Austrian Empire, and then just between us, there's still an Austrian Empire, just a bit smaller than it used to be. Hope there are no Austrians offended by saying that. It's a fact. So let's go a little bit bigger and ask you another question. Who of you has thought about the Roman Empire yet today? I want to see hands, okay? I want to see hands. I did because I went through my slides. Okay. Well, not too many. The meme is dying off, clearly. Okay, that's the Roman Empire. But let's go even back further in time, to the Trojan Empire. So I'm sure everybody here knows the legend of Troy. The war between the Greeks and the Trojans, where the Greeks besieged the city of Troy for 10 years. And at some point, they put this giant wooden horse in front of the gates where they hid their army, or part of their army, obviously, because it was still a reasonably sized horse, but not too big. Put part of their army inside of the horse and let the Trojans bring the horse into the city. That way, they breached the walls and eventually sacked the city. Now, at that time, there was a priestess in Troy. Her name was Cassandra. And Cassandra was a priestess of the god Apollo. And she made a deal with Apollo. Apollo granted her the talent of foresight. She was able to predict the future. But there was a little detail, there was a small print about that deal, which was that she would engage in, say, physical activity with Apollo. Let's put it that way. And I read the code of conduct. And so, she got the talent of foresight, but then she didn't actually follow up on her side of the deal. So that naturally pissed off Apollo a little bit. And Apollo cursed her. And he cursed her such that she would keep her talent, but nobody would ever believe her. So when that horse showed up in front of the gates, Cassandra went like, don't bring in that horse. The whole city will get sacked. But nobody believed her. And Troy was lost. And who knows? Maybe we would still have had a Trojan Empire had we listened to Cassandra at the time. I'm telling this story for a reason. For fun. In AI, there exists something that we call the Cassandra problem. And that is the problem of knowing which model will be right when. And that is a general problem in ensemble learning. It's an even bigger problem in decentralized learning, because in decentralized settings, you typically have no insight, no knowledge of what goes into each model. So you can't tell who is going to be right when. And that's particularly important because most models have a form of domain expertise. Like no model is the best always. Right? So there exist regimes where some models are better than others. And it turns out knowing that, having insight into that, is a way of much better coordinating a large swarm of models. And that brings me to the empire of 2026. We know these days that the solution to all of the failed empires in the grand and sad history of humanity is, of course, this bottom-up empire. Right? We all know that. You can create self-organizing structures from the bottom up with feedback loops, with regulation in it, that basically learn to organize themselves in ways that then benefit the larger structure. We call this networks. It can be hierarchical networks, it can be just pure peer-to-peer networks, doesn't really matter. But the way to actually sort of institutionalize and coordinate these types of structures these days is by building these types of networks. And I'd like to just discuss a little bit of the things I've just mentioned in the context of financial markets. Of course, NumeriI does a lot in that domain, and I think it's a natural sort of step where I think a lot of people here are maybe familiar with what I'm about to talk about. In financial markets, as I already said, but in general, but also in financial markets, models often exhibit a sort of form of regime-specific outperformance. Certain regimes within certain models are better than others. So if you have a model that does really, really well in one domain or one regime, you wouldn't really want to make many copies of that because then you would fail in another domain or another regime. You would want to know which model is best with. And this is not really a new problem. Like it's I think, new in the context of decentralized AI. But in AI in general, in ensemble methods, it has existed for a long time. Like at IBM's research center, they were doing sort of performance prediction in ensemble methods already in the 90s. So this is like not new in that sense, but what is new is trying to apply this form of figuring out who is good when in this decentralized setting where you have absolutely no insight into what every individual model is doing. And that's the problem we've been trying to solve with Allora is, what if we can find a way to solve this problem and capture all forms of regime-specific outperformance? So we create a network that learns over time who is good when, and that way becomes context-aware. So here I'm showing a lobotomized version of Allora that doesn't contain our solution yet. But let me talk through that briefly. So we have here Allora as a blockchain that is subdivided into topics. And topics are basically parts of the network that contain participants that collectively try to solve a single specific problem. So that problem could be anything, but let's say it could be predict the Bitcoin price in 1 hour from now. It's one problem. So let's say there was a request come in, and then we have a bunch of inference workers that make predictions, and at some point, so they post these predictions to the network. At some point, there was some ground truth that becomes available. We know what the Bitcoin price actually is in an hour from now. And then these inference workers are being scored by the computers here. That information gets passed into the network, and the network says, okay, I now know how good everybody is. I distribute rewards based on that. I get into more details later, but I distribute rewards based on that. And most importantly, I weigh all of these contributions according to the historical performance of all participants. Right? So maybe model A has been like scoring a loss of -1, and model B has been scoring a loss of -0.5, and based on that sort of average historical loss, I can assign more weight to model A. But that doesn't do anything with the sort of regime-specific outperformance that I was mentioning. So that's what we now did with Allora, is we added a second class of worker to the network, which we call a forecasting worker. And what the job is of that worker is to forecast the performance of every single inference worker under the current conditions. Because forecasting that performance, or the accuracy, the loss really, is itself a machine learning problem. Right? You kind of need to know, okay, what is my feature set, what describes the current conditions, and then I need to describe somehow, okay, who is going to do well under these conditions and why. And that then basically allows you to construct what we call a forecast implied inference. It's based on these forecasted losses, and that goes back into the whole weighting process. Let me talk to that in a little bit more detail now. So what a forecaster would do is it would use as its features, it would use the current conditions. I don't care how Like every forecaster decides that for itself, what it thinks is relevant data. And then the target is everybody's impending loss or regret under the current conditions. Doesn't really matter if it's loss or regret. And the network already has some defined rule set for mapping regrets or losses to individual model weights. That is what it would do naively without the forecaster role. It would take all of these inferences and combine them somehow in a weighted average. But now what we have is for each forecaster, we have a set of forecasted losses where every inference worker gets its individual loss. We can pass these through that mapping function to get a full set of weights and get this forecast implied inference. So that's basically how it would work in practice. And that's here schematically indicated. We put it. 3 workers provide raw predictions. The current conditions inform the forecasting worker to get weights, and then that forecast implied inference. It's maybe a little bit schematic. Let's take an example. Let's predict the weather. And I actually originally made this infographic when I was giving a talk where I wanted to predict the weather in London, and it was in February, but we're in Vienna now and it's March. So let's predict the temperature in Vienna in March, okay? So we've got 2 models. We've got Model A is a summer specialist. It's really good at predicting temperatures in summer. Model B is a wind specialist. It's really good at predicting the weather when there's a strong wind. So these provide their raw predictions for the temperature in Vienna tomorrow. And then the forecaster realizes, wait, it's March, and there's a strong west wind. I actually noticed it when I was driving here. I came from the west, and I almost used no fuel, which was correct, because fuel prices are awful at the moment. So it's March, there's a west wind, and the forecasting worker goes, it's March. Model A is going to be awful. So it's going to get a very high forecasted loss. Model B, well, there's a strong wind. Model B is going to get a low forecasted loss. So what that means is, low loss means a high weight, so Model B will dominate this forecast implied inference. And that then propagates further through. Here's another example. This is a financial example, which maybe is a little bit closer to heart for many here. So let's say we have 3 models where Model A is a bear market specialist, so basically doing well in downtrends, shown in red here in this diagram. Model B is a bull specialist, and Model C is a crab specialist, where the market's indecisive. That's like here, right? So normally what you would have is these models would just sort of point at each other like that, and be like, well, who's going to be right? I mean, I don't know. But now what we have is we have these forecasters that can actually learn who's going to be right. And what you can show is that if you have a naive sort of network inference that's synthesized out of all of these individual inferences, it requires time to learn who performs well during the regime that you're currently in. So it doesn't actually respond that quickly. But now that you have the forecasters, what they do is they characterize the current market regime, and they have already learned that, oh, we're in an uptrend, so Model B is going to do well. Oh, we're in a crabbing market, so Model C is going to do well. And what that means is you get the context-aware forecast implied inference within your network, which the network then, together with all other inferences, can synthesize and go like, oh, it turns out that forecaster typically predicts the losses really, really well. So therefore, the forecast implied inference coming out of that forecaster is really, really accurate. And it turns out I should be assigning that one a lot more weight rather than Model B, because it's not always a bull market. And that is something you actually see here. Maybe if you squint a bit, the screen is a little bit small, but basically the dashed line here is your naive inference, and this line here is the forecast implied inference. The blue line is the ground truth, and you see that both solid lines track each other much better, and the dashed line is lagging a little bit. And that is because the naive inference would need to learn what regime we're in very, very slowly. Now, you can put that together, and what you get is self-improving context-aware swarm intelligence, where the context-dependent performance forecasting allows the network to outsmart everybody. So this is an experiment I did in the 2024 paper where we published this. But basically, you get your raw inferences here. Your naive network loss, where you don't use forecasters, is sort of on par with the best one. But then you add the forecasters, and your full network loss does much better than anybody. And actually, there are parts where it just outperforms the best forecasters. Okay, now the question is, of course, how do you incentivize this? Because, of course, you don't want somebody to say, like, okay, well, I've got the best model, I'm just going to copy that 100 times and that's it. No, the mechanism I'm describing relies very, very strongly on model diversity. You don't want many copies of the same model, even if they're awesome. You want, like, it's better to add one poor model that is Cassandra, is just really good when it sees a wooden horse outside of the gates. It's much better than having, like, a legion of 100 awesome models that don't recognize a horse, right? You will want to have that one Cassandra always. So we try and incentivize the uniqueness of the models. So let's say you have your traditional network inference here with 5 models, generates a certain network inference with a certain loss. Now what we do for each model is just remove that from the calculation of the network inference and ask, okay, if we were to remove that model, how would the network inference change and how would the loss of the network inference change? And then it turns out, in this case, I remove model C, the loss gets worse, the network is worse without C, we need model C badly, and C gets rewarded for its contribution. So what that means is, in this case, on Allora, the inference workers do not stick. It's not possible to buy dominance in the network inference. They strictly get rewarded for their unique value add in network inference. So with that, we are now have a fully on-chain decentralized network with continuous looping inference, transparent data. All the inferences get committed on-chain, and the inference synthesis mechanism actually also is calculated on-chain. Generated over, of the order of 700 million inferences by now. I've received inferences from 300,000 workers across 55-ish, a bit more by now, of these topics, of these sort of problem-specific topics. And I focused kind of on financial applications here, but of course the kind of like what you just mentioned during your talk, the applications are of course very wide for any type of quantitative inference, right? So this extends to logistics, supply chain, healthcare, weather, etc. And our vision for the future is really to have this form of continuous inference as a new paradigm for machine learning competition between models. Because yes, the network is greater than the sum of its parts in a way, but it's also a way for individual model creators to really participate in the frontier of collective swarm inference, but also to find a way of actually competing in that environment. So what the network does is it does real-time scoring whenever the ground truth becomes available, and we have open participation, where the testnet is just open to anybody, and then based on performance on testnet, there was a rule-based promotion to mainnet. And that is what I'd like to dive into during the final part of this talk, is a platform we've created that's called Allora Forge. The Allora Forge is basically a platform where machine learning engineers or model builders can build, test, and deploy their machine learning models end-to-end on the Allora network. And that way, it's basically it's a trial ground for model creators, right? Where you can really prove yourself and show that you're worth participating in the Allora network as an inference worker. So it's a full stack platform. Everything that you need in principle is on there, and it's open to anybody of all levels, novice to expert, to basically participate. So we have built-in Jupyter Notebook support, full Python ML framework. It's also AI native, so we have Allora skills created that basically allow your favorite coding environment, Claude Code, Codex, whatever, to very quickly pick up and generate competitive ML models that are great at whatever problem you're trying to predict. We've tested them on financial price forecasting. It's working really well, actually. Then there is real-time scoring. So you get your feedback loop on how your models are doing live competition scoring and grading. It's on-chain, so there is consensus about the predictions. They're all validated. And you can use these competitions on the Allora Forge to compete for rewards, be part of a community, and interact and enrich your entire workflow by communicating with all of the ML innovators that we have. So the way this works is we have what I just discussed with the on-chain Allora network, which has topic contracts, competition topics, has the consensus mechanism that validates the predictions, and then manages the whole reward distribution based on the model contribution to the network inference. And then the inference worker is an off-chain node. It contains your machine learning model, make predictions about whatever the topic is. It runs inside a Docker container, so you can deploy it anywhere. And it uses the native Allora client to communicate with the blockchain. So basically all the hard stuff is abstracted away. That's all basically automated. It's a very simple, like, few-click workflow. And then we run competitions within the Allora Forge. So these are basically open source hackathons where you can participate in these sort of prediction matches. And yeah, you're competing to produce the best model. And we launch these competitions regularly. They run for like 2 months and up. And they map directly to current or upcoming prediction topics on the Allora main engine. So by basically participating in the Forge, you're then ideally positioned to take up a role on Allora mainnet. And the participants are whitelisted for mainnet based on their level of performance in the Forge. And we have, as mentioned, we have basically an automated evaluation loop there. So here's an example. Let's say you have a competition that's a 1-hour ETH/USD pair log returns prediction. So what you would do is, say, every 5 minutes, you would submit your inference. Okay, what's the ETH/USD log return going to be in the next hour? You can use historical market data or whatever other data you want to use. Allora is completely data and model private because the only thing you submit is your inference. And then indeed, the models are evaluated on a bunch of different metrics. I have a full list here. I don't think I'm going to talk through this fully, but in this case we have a log return. We developed a specific loss function for log returns. Turns out if you use traditional loss functions on log returns predictions, they actually do really poorly. They kind of emphasize the wrong signal, and actually, if you just predict 0 log returns by default, most loss functions will actually promote that over other things you can predict, which is, of course, is not very informative. So we developed this new loss function that we called SAR, or Composite Zero Agnostic Returns. It's something I got from astrophysics. We have all kinds of nonsense acronyms there. So I thought it would be fun to apply that here. And yeah, then there's a bunch of metrics that basically, when satisfied, it qualifies for a mainnet slot. And yeah, so what are the participant benefits here? I think it's multiple. You earn rewards and recognition within this framework, within this platform. You can earn a worker slot, and then that gives you the opportunity to actually earn real allo the moment you're on mainnet. There are public rankings where you can compete and rank yourself, kind of like with Kaggle, but on-chain. And basically your scores will be mapped immediately to your profile. You're joining a big community of ML innovators who are basically collaborating, expanding expertise. The Allora engineers are active in that community as well, so there's a lot of exchange there. And as mentioned, we've developed a set of skills that are basically just directly insertable in your favorite LLM coding framework. And of course, show it off on LinkedIn when you're doing well. So I'd say, this is the end of this little ad, but this is where all the fun happens, okay? So you should join us, join the dark side. Okay, I'm gonna wrap up here with some concluding remarks. What I mentioned is that Allora's long-term vision is a form of continuous inference as a new paradigm for machine learning competition. Open and fundamentally meritocratic. And Allora's unique forecaster role has solved the Cassandra problem. We now have context-aware inference synthesis that actually lets the collective outperform the best model within the system. And that is one of the most attractive things here, is that you basically have the opportunity to be rewarded for what you do, but at the same time contribute to that. So basically, it cuts both ways. The Allora Forge is your entry point into Allora. It's fully AI and skill-enabled, and it supports the entire cycle going from an idea to a model to deployment to then earning on your original idea. And that way, it's a unique opportunity to both monetize your model's performance and also contribute to this frontier of decentralized swarm intelligence. So if you want to know more, I got the link to the Allora Forge here, so forge.allora.network. And if you would like to know more about some of the research papers that I discussed, you can read up in our Allora Decentralized Intelligence Research Journal, allora.network/research. And to my knowledge, this is one of the few, if not the only, journal that is specifically focused on decentralized AI. It's why we founded it, and it's not exclusive to Allora. So actually, also, if you have a research idea where you're like, hey, this is actually relevant to just decentralized AI in general, and there's not really a good venue for me to submit that to, come talk to me, or ping me on Twitter, whatever. Yeah. Thank you very much for listening. Please.
Thank you so much. When you said before for a part of financial model, you can also apply for medical.
Yeah.
You also have experience with with
So-
structure, for example, because you said, with machine learning.
So, fundamentally, it's a great question, thank you. Fundamentally, the infrastructure that we've built is domain agnostic. So basically what we've done is we've built a coordination layer where you can define a topic that says, okay, predict this on this cycle, this frequency, that much into the future. And you can then basically solicit inferences from a population of models, and it doesn't matter what the domain is. So what that means too is we rely on the community for domain expertise. So the moment that we have a competitive community in that specific domain, we can spin up a topic and just do it, right? And that's kind of why we're starting in the financial domain, because that is where we have that type of community. But fundamentally, it is possible anywhere. Yeah.
Yes, because for example, I know here in Vienna also there's a lot of things related to SQL structure, for example.
Yeah.
And when you were saying this, it's like, wow, sounds nice, no?
Yes, yeah, absolutely. Yeah, so I think it's, yeah, I mean,
Yeah,
it depends on details, but in principle, yeah, that would work. Yeah. Please go ahead.
First of all, I find it excellent that here, and we need more live competitions in a way, right? Technically, I have a question. So, when you submit these predictions, how does this technically work? Is the model run on your infra with the new data, or like, does it need to be an API endpoint where you're pulling that from?
No, fundamentally, all you need to do is commit the inference to chain. That is fundamentally the only thing that is necessary.
Inference means what? The predictions?
Yeah, the prediction.
Yeah, okay. You need to do this every 5 minutes?
Yeah, like if it's a 5-minute cycle, then you need to do it every 5 minutes. If it's a topic with a 15-minute cycle, you need to do it every 15 minutes. Having said that, we are thinking about hosting infrastructure as well, right? And then, yeah, you could basically, like, then everything becomes self-contained. But, yeah, that is currently being discussed. So I think actually, I technically should stop there. but it's definitely something we're thinking about. It's just that regardless of how that particular detail works out, it's fairly light on the modeling side, right? Because either you do everything the way you want to do it and then you just submit a prediction, or you can just run everything within the platform. And in both cases, you don't really need to worry about it.
And the data that goes into the model is completely on the end user side.
Yes, yeah. It's
So I can take Polymarket CLI and feed the predictions back into
whatever you want to be using. Yeah, and it's completely data and model private as well, so nobody else would know.
Okay.
Yeah. More and more answering.
Yeah, I didn't fully get, so with the Forge,
Yeah.
you need to do well there to be promoted to the mainnet.
Yes.
Is that per topic? Or is once you're promoted, you can...
That's a great question, and I have to admit internally that is a little bit of a moving target. But we're deliberately setting it up now that there is one-to-one mapping between testnet topics and mainnet topics. So that basically, if you qualify on one topic, then there's a natural way forward for you. Because domain expertise is domain expertise, right? And it doesn't really make sense to just do a blanket whitelist if somebody was good at one thing. So yeah, so we try to preserve integrity a little bit that way. But I could imagine, for instance, that there were some topics that are so adjacent that one would qualify for more. That would be on a case-by-case basis. Please.
A question about the forecaster.
Yeah.
So what's the shape of the input?
That's a great question. Forecaster. So actually, yeah, I didn't talk much about that. I mean, with Forage, I kind of said this is for inference workers. What I should add is there are fewer forecasting workers than inference workers, and we don't really have a whitelisting procedure available for forecasting workers yet. But it doesn't mean we're not looking for really performant model builders who could build forecasting models, right? Because we've built our own, and there were some other participants who have done that, but somebody's like, that's actually a really interesting problem to work on. I'd like to build a forecaster node. Come talk to us as well. And Tim is in the back of the room as well. I can talk to either of us. Now to your question, so the feature set of forecaster would typically be a combination of what we call public data and private data. Public data would be anything that's recorded on the chain that relates to the technical performance of inference workers. So their actual inferences, the losses, the regrets, but then the contextual information based on which you can say, okay, these actually change in certain ways, that would typically have fairly high overlap with the feature set of the inference workers. Right? So if I were to spin up an inference worker that just predicts, I don't know, Bitcoin price or my heart rate after I finish my talk, then that forecaster would basically benefit from using a fairly similar feature set. Right? If I take the weather in Vienna example, like the forecaster needs to know that there's a west wind, and probably the individual weather models would also know there's a west wind. So there is some overlap there.
So the question really is, for inference, you mentioned that it's completely data and public, right?
Yes.
Any data you want.
Yeah.
For forecasting, is Allora going to give the forecasters some data, or is that also bring their own data?
That is bring your own data as well, although we also do a form of data provisioning where we actually try, so we do both. But obviously the edge doesn't exist in the data that Allora provides, unless you do some very smart feature engineering on it. But it's in principle it's data that is available to everybody now. So there's always an edge in having your own data processing to some extent, unless you do TAPI event, of course.
But you need the data.
Yeah, you still need the data.
That's the thing.
That's right. Yeah. I'm coming to you in a sec.
Just a quick
Oh,
one.
sorry.
When we are financial markets and you said you have those
Yeah.
three, the bull,
Yeah.
but in the moment it goes from a crawl to, let's say, a bull, you don't really know when this
Sure.
is happening, right?
Yeah.
This is like the anticipative thing is not solved, or is it solved with this one?
Depends on whether how predictive your forecaster is, right? So if the forecaster characterizes not just are we in in what regime are we, but what regime are we about to enter, then you've solved that too. But that's the nice thing about ML is that you could solve that too.
But then you need a forecaster's forecaster.
Yeah.
Okay, I'm gonna admit I've gone there. I've built like a hierarchy of forecasters. Yeah, sorry.
Yeah, so this sounds very familiar to anyone who knows about predictor on ocean protocol. But the difference here is apparently that you have a meta model. My question is, with crypto forecasts, do you have already any history of your performance of the meta model?
Yes.
Do you have any results?
Yes. I mean, it depends on the specific one, but we regularly publish the results on our Twitter channel. But to give you an example, what we typically do is every week we publish like the top 3 top directional accuracies across all topics.
Yeah.
And that varies, of course, greatly, but typically between, like the top ones are typically between 55 and 60% DA.
That's for Bitcoin.
Bitcoin, Ethereum, Solana, different time frames, but it depends on the time frame and the asset, which one does well when.
The question is that performance of best predictors or of your meta model?
The meta model.
Of your meta model.
Yeah, it's the network inference.
Okay.
Yeah.
So the submission workflow. You have a Python library for that.
Yes.
Does it have dependency on Web3?
The user doesn't need to be Web3, have any Web3 knowledge fundamentally.
It's okay, but is there dependency in the library? Because it's a massive dependency, it's very difficult to work with it.
The library is intended to work with the Allora network, and the Allora network is a Web3 network. So there is an actual, but Tim, you want to comment on that?
I'll just say I'm doing a workshop later about exactly how to set up a worker to submit inference and what's the definition of Web3? You do have to have an address, right? So we'll talk about setting up a wallet, but you don't have to. It doesn't have to work in a website, for example. You can do it in in any computer. So we'll talk about that this afternoon. Yeah.
I saw one more, 2, 3, 4.
Can we have just two more questions? Sorry.
Okay. Well, everybody come up here and fight over it. You want to go?
So I learned about Allora a few days ago and about Allora this morning, so it might be a stupid question.
I'm sure it's not. So
Could you run the Allora tournament use case on top of Allora?
Yes.
I mean, what is the main difference between this topic and the subnet in the tensor?
I think they're fairly analogous concepts, although the projects themselves actually differ quite fundamentally. Like, BitTensor uses a fundamentally different way of evaluating model weights. I mean, from a traditional economics perspective, like BitTensor is a beauty contest, right? Where you're trying to predict how everybody else is going to value something. And then that way stake on others, right? That is fundamentally what BitTensor does. And what that means is there are financial incentives that determine model weight. And kind of the main point of Allora is that is not possible. It's strictly meritocratic. And the whole incentive structure is aimed at promoting that. So fundamentally, you need the topics, or in BitTensor's case, subnetworks, to generate the domain-specific infrastructure that you can use to then coordinate models. But then what subsequently happens is completely different. Yeah, I'll stop there. Come see me after.